Here we go, back online. So you just missed a little bit of architecture. Sorry for that. So once you arrive at output stage, again, I don't want to squeeze the details out of here, but link to information that you might find useful. So in this case, the original paper, we predict output probabilities. Because we feed this through the softmax function again, and softmax you have now seen in repetition, which means we have to compare potentially probability distributions or labels in some sort, right? So cross entropy for classification we've come across before. Maybe you have also heard about the Kullback-Leibler divergence, but we don't have to dive into this today, but it's certainly important to hear about at some point if you haven't. So I linked a blog post here. Maybe I come back to this concept later next week when I talk about weather forecasting. I have to see if this will be important enough to devote maybe 5 or 10 minutes to this. Okay, would anyone like to have a 5-minute break, given that at least one person needed it? Or shall I just continue? Okay, it seems like you are at least keen to continue. So I will try to finish a bit earlier. Let's see, I can probably speed up on the climate modeling a little bit. Okay, so what are the key benefits? We have no recurrence, but we have attention is all we need, right, or you need. So we can compute this in parallel. You get short paths across the network, even for long-range dependencies, which is really a key improvement over, let's say, recurrent layers, but also convolutional architectures that were suggested before. And the attention reveals also quite literally what the model is paying attention to. So it delivers a level of interpretability which is unusual for such complex neural networks. The main downside for practical applications is it's very data hungry. So people tend to write, talk, and talk a lot, but Earth is sort of patient, right? So not every application it's perfectly suited for, just as a little warning. But climate model emulation might be a good one, actually, because you can create samples very quickly, right? Because you can let a computer do this. Okay, so a few practical issues coming to time series prediction using these sorts of methods. You might ask, okay, transformers, interesting, but I'm here for climate and environmental science. I'm interested in time series. Fair enough. So if we are at time t and we want to predict output sequence from now on, then you often have this issue that we need future outputs. So if we do this autoregressive feature with outputs being right in here, sort of shifted by one time unit for the future. So let's say you want to predict the next 10 time steps. This might be difficult if you don't have that information, right? But you are in that position, let's say, for a weather forecast. So we need, what typically is done is this auto-regressive idea that you fill in this information by the predicted outputs. That's clearly a problem if your predictive distribution is somewhat drifting away from the actual problem. So natural language processing, it seems to be less of a problem in domains that are less well constrained, or have more openness to points that have not been observed. You might not model this distribution perfectly, and you have sort of, a scientist would say, error accumulation, right, in each step. You make a bad prediction, you feed this into the next prediction. So this is something called a distributional covariate shift. So you could literally drift away from the training distribution and get worse and worse predictions. So one of the architectures I discussed briefly next is sort of trying to pick up on this to a certain degree, but I guess the possible fixes to this are quite intuitive in the sense that you could make the model non-autoregressive. So instead of generating one data point after the other, you could just predict all data points in one go. So instead of saying, I predict the next word, I predict the next 4 words at once if I'm interested in the next 4 words, right? And you could just set your training data up in this way. But yeah, it depends on your problem if this is particularly skillful. The other idea is that you say, okay, if I don't observe enough in the training data to be able, once this distribution shift happens, that this then drifts away, could I create a training data set by making it artificially worse to emulate this situation so that it becomes more robust to feeding itself with worse outputs, so to speak. So you could degrade the quality of your outputs by adding noise that seems to mirror this distribution shift so that the model learns to correct for it. Okay, how to implement this? Relevant information maybe for assignment 9. Transformers are so popular, you will find PyTorch implementations, also pre-trained models pretty much everywhere very quickly. It's mostly sort of overcoming the initial inertia to do so, and decide if you want to use TensorFlow or PyTorch packages for this. I linked to a few Jupyter tutorials and websites here, also going through the original Transformer paper, if you are interested in exploring this. Yeah. Okay, any questions on the Transformers to this point? No? Okay, so, sorry, you were outside, and I appreciate you needed a break. We had a vote, and no one else won. Yeah, so we just continued. I hope that's okay. Okay, so to bring it closer to what I'm interested in, Transformer and the attention mechanism is clearly very important. I also wanted to briefly talk about an architecture that uses some of the Transformer ideas, but is more adapted to some of the actual forecasting problems that we have to face on a daily basis. And that's the temporal fusion transformer. It's meant to be even more interpretable. Okay, so interpretability plays a key role. Multi-horizon, which means it wants to do this thing of multiple time steps into the future, and how do we do that if we don't have future information, or can we take information from the future into account, which the classic transformer doesn't necessarily. The original setup, well, maybe indirectly you could set it up this way. And then also multivariates. Usually we have multiple variables to predict as predictants, predictors, and then a scalar predictant. But you could also scale this up to multiple predictants, I suppose. So what the TFT can do, it is more adapted to the time series case in the sense that it doesn't just take past target values with a look-back window of a certain kind into account. This is illustrated here, right? So this would be the past targets. You had a forecast time t, and you want to make a prediction over a certain time horizon. You have prediction models that takes inputs, and some of these inputs can be observed inputs, so something that we know about the past values of, right? So past meteorology, let's say, that you have observed. But then you also can take into account known inputs, which can both already be observed, but also can cover future ground, right? So if you, for example, say we want to predict traffic or we want to predict pollution, then maybe on times of day or weekdays where you have commuting hours, you can already say that on that day there will be something different, right? It might be particularly busy, particularly polluted, or if you know bank holidays, it might be different. So you can feed known inputs into the future prediction because you know those values quite literally. I'll touch base on how you can also use slightly degraded information as known future inputs. And then what it also does, and this is quite relevant for problems where you don't want to predict for an individual station, for example, measurement station, but want to learn station characteristic static variables as well as your predictors, then this is also possible with the TFT. So that's a huge advantage because you will see an air pollution problem later on. You might have local population density that is fairly stationary, right? Or you might have local orography, like on which altitude are you? And this way you can learn over multiple stations or multiple points that share certain, that are different in certain static variables. And you can basically include those conditionally in your data set. And you don't just have to have time varying variables. They're included in quite a natural sort of way and separately, so that it makes sense to be fed in again at various conditioning stages. And the output, and this is again nice, it's probabilistic. So they use quantile regression here. So you basically try to predict prediction intervals. So you predict a 50th percentile prediction, right? And you might also predict the 10th and 90th percentile distribution, which gives you at least an empirical confidence interval, prediction interval in what is being put out. And if you want to write this down as a formula, you basically try to predict a certain scalar value in most cases as a function of a quantile dependent function of the previous values for what you try to predict, variables that only look back in time, right? So known observed inputs, and variables that sort of known for the past, but also known for the future, and some static variables. And later on in a figure, this will be partly subsumed into different letters. But I just wrote this here for you to be later on be able to use these slides and match one thing to the next quite easily. Because when we look at the entire TFT architecture, it becomes very quickly quite complex. And you could, when I look at these sort of plots, I think an AI method might learn quite easily to build even more complex architectures, right? Because at some point we become a bit limited by what we can imagine and still think about. But sort of a few fundamental ideas of this architecture to make this possible is that it integrates mechanisms of multiple neural architectures. So in this case, you still have LSTM components included for good reasons, as they argue, but you also have these attention heads from the transformer architectures, okay? And just to highlight a few things, on the left side you have the static covariate encoders, which integrate the static features at multiple places, both at the beginning, sort of bottom layer of the inputs, but also later on in this sequence-to-sequence layer, and also one level up when you go into the decoder level. And what happens at the base is you have a variable selection, a neural network that does variable selection on a sample-by-sample basis. So you basically learn already on a sample basis what information do I feed in the network at all. This is sort of a dimension reduction or sort of pre-sorting approach to I guess it addresses in a way the curse of dimensionality. It also later on serves for an interpretability feature because it allows you to derive global feature importances for predictions. And then you have the sequence-to-sequence layer, which is composed of LSTM encoder-decoder structure. So you can look at these for a very long period of time. But the idea behind using an LSTM here again is the time order in particular, and also the structure of having inputs that are partly based on sometimes based on the past and sometimes also extending into the future. So you have a slightly more complex data structure, but fundamentally an LSTM picks up on data structure, right? So it knows about the time order, and this helps you to learn the short-term dependencies. So basically what the TFT does is to break it down into two aspects where the sequence-to-sequence layer is meant to pick up on short-term dependencies, and this multi-head attention is doing the long-range part, okay? And then you also have a few tricks like gated residual networks, which just allow you to have skip connections to make your fundamental network architecture, if it's not needed, far more simple, right? So you have certain gated mechanisms and residual connections and so on that allow you to basically simplify the network if it's not needed at such a level of complexity. Okay, I think the paper is really worth reading. So I've linked on the previous slides both to the original archive paper and the recent journal forecasting paper. But the key take-home message is, without spinning this for too long, is that you can it's highly adapted to the time series case in the sense that you can take static variables into account, which is very important if you want to learn about data where you measure, for example, at different points in space, that there are static features that make those measurements different, but you still would like to learn across all of those, if that makes sense. And then that you can also take known future information into account, weekday, bank holiday. In different cases, it might also be a weather forecast, right? So we used this when we wanted to use a machine learning model to create an air pollution forecast. We said, okay, well, for the air pollution forecast, why do we not also use what we already predict for weather in the future, right? So you could take this weather prediction into account. It's not ideal because the forecast won't be perfect, but it's information you have about the future values. And then you also get probabilistic intrinsic uncertainty estimates out of this in the quantile regression. And maybe the key idea, and I will show you an example of this, is that you have better interpretability. So the variable selection blocks that you have at the beginning here, they allow you to estimate global feature importances, similar to what you had in random forests or some of the explainable AI methods. And then also they use an adjusted definition of the multi-head attention. I didn't really go into this, but it shares the weights used to multiply, to get the values across multiple attention heads. And this allows you, instead of having a sort of very different scale attention heads that are not easy to sum up, as in the NLP example earlier on, it makes it more comparable. And you can literally look back in time and plot the attention what days, for example, or which steps in the time series the TFT paid attention to. And again, there are fairly intuitive implementations of this already, and maybe even more applied to actual problems like climate model emulation that you might want to try out using PyTorch, for example. So, okay, so the TFT might be something you want to try for assignment 9 as a result. Note that in climate model emulation, you could also take future inputs, basically, because they will always be there, because you emulate. So you're not making a forecasting task as such, so it makes it sort of interesting. I wanted to try this for a long time. So if you want to be the people to do so, I would recommend, because these neural networks are expensive to train, you could look into something alternative to grid search CV or manual typing of the hyperparameters, okay? And there are clearly a lot of different options here. I'm sure you've heard about some of these before. And I think it's just nice for you to explore those. I linked two options. Random search is one. It's not particularly a smart way of doing it, but you can imagine instead of using over the entire grid, which scales exponentially in number of combinations, you could try to test random subsets of those combinations. Bayesian optimization tries to be a bit smarter about this by looking at how did past hyperparameter evaluations in combination perform, and can I use this to choose my next hyperparameter combination that I want to try. So you can even use scikit-learn for this. And I also linked to a blog post here which shows a few examples. I think this is best learning by doing, but assignment 9 gives you a perfect opportunity to do so and to speed up your cross-validation a little bit. Now, I know about a recent method that does something different, something similar, but based on an evolutionary optimization algorithm that was produced here in-house at KIT in the SCC. So I link to this as well, but it might not be the natural starting point if you haven't done it before. But for future work, I think it's certainly a method I would recommend looking into. So one bachelor student actually currently does this. I supervise. Okay. So just to give you one example of this, I'm afraid this took me far longer, which means the climate modeling time will be a little bit squeezed. But you've heard about Sepp Hickman's work if you attend the exercise class. Attended this particular exercise class looking into air pollution forecasts for ozone in Europe. So he had a massive data set of billions of data points for ozone pollution in Europe. And he said, okay, can I use such a TFT to predict air pollution at different stations 4 days in advance? So what you would get in terms of interpretable ideas here, you are at time step t equals 0, right? And you try to predict the next 4 days. So observed would be in blue. The predicted values using the TFT in orange, this would be the 50th percentile. And then you have different percentile ranges in different shadings indicated as well for your uncertainty. And in gray, you see the attention that once you have this simplified multi-head attention that you can summarize what days in the time series, in terms of the input features, the lagged input features, did the network, the TFT, pay attention to. And you can see this is a fairly high pollution day, so the attention is high on previous days that had a fairly high pollution, at least a few of those. And vice versa, Sepp also showed the opposite for days with low pollution. So that's exactly what you would expect. And in terms of global variable importances, you can also get something that you are maybe already used to from a random forest regression or so. So you get the decoder-based variable importances. So in this case, planetary boundary layer height was very important, temperature, wind velocities, and so on. And Sepp showed quite convincingly that this can clearly outperform some of the baseline methods that I would usually recommend to fit on such problems. Okay, so let me try and get through this in 15 minutes or so to give you more time off because you didn't take a break. I promised to talk about climate modeling a bit more, especially in the context of assignment 9, where you used this, but you also used climate model data in Hackathon 4 and various other places of this module. And you've come across this coupled model intercomparison project, or CMIP, quite a bit as well. And CMIP itself defines itself on its website as its objective being to better understand past, present, and future climate change. And this climate change is not necessarily only driven by humans, but could also be natural unforced variability, or driven by humans in response to radiative forcing of the Earth system. So that's already a slang term that you should be familiar with, because I talked about this in lecture 4, 5, something like this. So radiative forcing is we change the composition of the atmosphere, aerosols, CO2, methane. We change the Earth's energy balance. So we have a radiative forcing by changing how much the energy balance of the Earth's atmosphere or the Earth system, because it's not just the atmosphere, actually. The energy is then distributed through the entire system. And it also adds this term here, multi-model context, where we have to be careful, because models have very, like, especially in my field, right? There are many different types of models, right? Basic statistical models, machine learning models. So multi-model context here means multiple climate models. Okay, so these physical process-based Earth system models I will talk about later on, which in turn have many sub-model components which are for themselves probably models, you could say. So how do they define understanding? They say we want to assess model performance during the historical period, because clearly that's what you can benchmark your models against. So we are used to that sort of concept also for machine learning. We want to see is our model doing well against clear metrics that we want to perform well on. So this is climate model evaluation. But we also want to quantify causes of spread and future projections for which we don't have observations, right? And that's very important because, as you will see, these models do give you different results for the future. And this is what we call model uncertainty. So quantifying the spread, but also understanding the spread to then be able to reduce this uncertainty is one of the key tasks. Now, what is not necessarily self-speaking, I would say, but is clearly the case here and for a very long time, is that all this model output is available online for everyone to use, right? So it gives you a massive, I don't want to use the word playground, but it gives you a massive big data archive in a very standardized format that you can use to try and understand climate change better and what we're doing well or not doing well. Now, the term global climate models is something that is a little bit frowned upon, sometimes in the climate modeling community, in certain parts of it. 90% are fine with it, but some very sort of hardcore physical science people would probably say, I'm a big fan of a global atmosphere-ocean coupled, they would call it an atmosphere-ocean general circulation model, because it all started off as general circulation models, which were sort of fluid dynamical models of the atmosphere and the ocean. Later on, atmosphere-ocean, this was the coupling of the atmosphere and the ocean, right? And then you had to think about all these different aspects that are important, and only over time we were able to describe in a better way. So you have to describe the atmosphere, you have to describe the ocean and the sea ice, right, swimming on top of it. You have massive albedo changes if ice melts from white to blue, basically, right, or depending on your water color. And you might also want to model the biosphere, especially for the carbon cycle. That's important. How much of the CO2 we emit stays in the atmosphere. The biosphere also has, you can see this in cities, right? We've seen talks about this. Bespea as well. Vegetation can have an impact on local temperature and the local energy balance. And maybe also in the ocean there might be a marine biosphere and so on that leads to how much CO2 is deposited in the ocean and so on. And all these processes you have to couple, maybe also land ice sheets and so on. And yeah, so the IPCC or the CMIP says we basically want to create computer models that create digital analogs to Earth's climate, which clearly also means you can't just look at a single ocean basin or so, but you have to run global models, a global system. The Earth system is a global coupled system. So if you want to look into this in more detail, the WCRP writes a short introduction on these climate models, and which are also somewhat in terms of a synonym, but that's not quite right. Necessarily there's a distinction referred to as Earth system models, but the idea is that you want to refer to sort of represent all processes that might be important. Let's say heat exchange between the oceans and the atmosphere, but also composition of the atmosphere, so atmospheric chemistry, clouds, right, very important, interaction with the hydrological cycle, and so on and so forth. And we also have entire model to comparison projects just focused on seeing can these models reproduce a response to a major volcanic eruption that had an impact on climate. So all these processes have somewhat got to be represented, and only if you have, so an Earth system model I would classically refer to if you also have an interactive carbon cycle, because you could have the choice to say the carbon cycle aspect, so how much CO2 that is emitted by us is so first of all, how is it redistributed between the ocean and the atmosphere, for example, but then also to the biosphere, right? How much is picked up by the biosphere? This usually requires some sort of mechanistic representation of the carbon cycle acting on very long time scales, and this usually makes it from a climate model for me to an ESM. So from a purely physics-based model to a biophysical model. And in these Earth system models, you often also have more comprehensive representations of other processes like atmospheric chemistry, for example. And if you look at the evolution of these models over time, then first of all, I've mentioned several times before that these are numerical models, so you solve them on a numerical grid, both in the horizontal and vertical dimension. You can have different sort of grid structures that might be beneficial in polar regions, where otherwise you have increasingly small grid cells, which can lead to reach something called the Courant limit. So these models have increased in resolution over time, increased in vertical resolution as well, and coverage, so the upper atmosphere was included. More and more models include, let's say, chemistry, ice sheets, carbon cycles, and so on, moving to full-blown Earth system models. And Hackathon 1 was about emulating one key component of atmospheric chemistry, ozone, using machine learning. And this is a slide I got from Peter Brasicki in IMK ASF. So clearly some of these models are also developed in Germany. So the flagship model is IconArt, where the art component specifically is pretty much an in-house development here at KIT, which is for atmospheric chemistry in particular, and atmospheric composition, which drives many aspects of climate change, but also important for air pollution forecasts, for example. And this all happens in collaboration with the DWD, so German Weather Service, and Max Planck Institute in Hamburg. And yeah, fundamentally, you can have different model resolutions, nested model resolutions. You can go up to around 80 kilometers, 75 kilometers in the atmosphere. There are certain configurations where you can even go into the thermosphere and study or ionosphere to study different types of chemical mechanisms, for example. But clearly also the horizontal resolution plays a role, because the horizontal resolution will ultimately limit what you can capture, right? So orography usually shows this quite nicely. If you have individual mountain peaks, like a little mountain top that is maybe, 10 square meters large, you will never be able to resolve this here, right? So resolution does matter, for example, for very regional phenomena. As you can imagine, and also processes we can simply not resolve yet, like clouds. Okay, so you can imagine we have a lot of these models. One is here in Germany, but there are Japanese, South Korean, models, Chinese, American, British, French, you name it, different types of models, and everyone develops their own version of this. And then you want to compare those. And if you want to make this in a conduct this in a systematic fashion, you have to define certain sets of experiments all these modeling centers run and then can intercompare. So this is what is happening in CMIP. And as I already indicated, in CMIP you have all these subMIPs like PMIP, which stands for paleoclimate, CFMIP, which stands for cloud forcing, I think, model intercomparison project, so focusing on cloud feedbacks and the uncertainties that we've discussed many times. Or you have scenario MIP, which looks into the future simulations, SSP type scenarios that you also, if you have already started this, see in assignment 9. And this shows an old figure relating to CMIP 5, where you just see that certain core experiments should always be run. This is also referred to as the DEC experiments. And these are consistent, at least the upper optimal time C on pre-industrial control run, which gives you a baseline, so absence of human influences, just a constant internal variability that modeling centers have to run again and again and allow you to keep track of different phases over time, especially moving forward now over the next few MIPs. So a little bit on history. CMIP started in 1995, established by the World Climate Research Program, which is still managing this. So the latest version was CMIP 6. Now, you might think CMIP 6 means there have been 6 phases in total, but no, we count here as 1, 2, 3, 5, 6. That's very special. So there is no CMIP 4. Good luck finding CMIP 4 data. That might be a challenge. And this was made mostly to bring it in line with the reports, assessment reports by the Intergovernmental Panel on Climate Change, or IPCC, because the CMAP experiment simulations, is maybe a better term to phrase it for the general crowd, is strongly informative of these IPCC reports, which really then receive a lot of attention. CMAP1 and CMAP2 were still based on a smaller set of models and just ran 2 sets of experiments, so a pre-industrial control run, which gives you a baseline, and then, because they said, okay, we don't really know in terms of scenarios yet, we just run a 1% increase in CO2, atmospheric CO2 per year, over 80 years. So ramping up a CO2 forcing and see how that changes for each model compared to the pre-industrial baseline. And since then, this has significantly evolved over CMAP3 and now CMAP5 and 6, with a lot more experiments, a lot more models. And CMAP7 is currently being planned. And I mentioned this in my first week here as well, that this increase in model resolution, increase in number of variables you're interested in for scientific purposes, increase in number of models, experiments, and so on, has led to an explosion in the data output from these intercomparison projects. So this is CMAP6, this is CMAP5, and so on. And you can clearly see similar trends elsewhere. So the latest generation CMAP6 had 132 climate models in some way contributing across 48 different modeling centers, so that's quite a big effort, as you can imagine. And then you have the historical simulations, one of which you train on as well for the Norwegian model in assignment 9, which is usually run from somewhere like 1850 to near present, which typically is in CMAP6 2014. And then you have all these endorsed MIPs that run different experiments, such as the scenario MIP for future scenarios. So just to very briefly touch on this, it's a standard way. How do you predict the future if you don't know what happens to us, right? What we will choose to do. So you can come up with a number of different scenarios. And again, you see this in assignment 9 for how, given different economic developments, socioeconomic assumptions, CO2 emissions might change at the same time as methane emissions might change or aerosol precursor emissions might change. And it ranges between a number of scenarios that sort of think of the worst case, often referred to as taking the highway, fully fossil fuel development of all countries to ultimate development until things break. And I guess that would have a self-regulating effect at some point, many people say, to a strong mitigation scenario, sustainability scenario, where you really try to push hard to let's say, stay below 1.5 degrees Celsius global warming. So I will not run through this in great detail, but if you look into uncertainty in future climate change projections, you have to pay attention to a number of different aspects. So you can, as I say, compare to observations. This would be for a grid point, including Karlsruhe. You've seen this many times before. And you have CMAP6 historical simulations, 34 I plotted here, on top of actual the observational data from the Climatic Research Unit. And then you can look at what these same models project for the future, let's say for SSP5, the high emission scenario, or SSP1, the strong mitigation scenario. And you can see that for individual ensemble members, for individual models, so there should be 34 lines each, there's a lot of local noise, right, and potentially uncertainty. So you can immediately say that if you wanted to say what is the warming going to be in 2050, you probably want to take some sort of average value because you have this high internal variability in each ensemble member, right? A year, this is annual mean data from these projections. A year can be noisy. And on top of this, you have model uncertainty. So this is typically what we refer to as internal variability uncertainty, that you have such a high internal variability noise. So if you could take this out, there's no magic wand to do this, but if you could, right, so some smoothing method, it would probably look more like this. And from this, you could then look, for example, at the median or mean value changes over those 34 models. And this is what we would refer to as scenario uncertainty. So for the strong mitigation scenario, you might end up at a significantly lower regional warming. Let's say, on average, maybe 3 degrees for the strong mitigation scenario and 7 degrees for the high emission scenario. But then you also have clearly this huge range of model uncertainty, which we try to address. So can we rein this in somewhat by looking at which models performed in what way better on historical data or for specific mechanisms that are particularly important in driving future uncertainty, such as clouds. And that makes a big difference, right, for, say, climate risk assessments and so on. So I will jump this slide mostly, just for you to be aware that why these physical models are important. They give you mechanistic insight, right, that you don't otherwise necessarily get. So if you, let's say, force such a model by a 2 times CO2 increase, so sudden change, and the system would globally equilibrate. First, there's a shock to the system, then it would sort of equilibrate to adapt to the new equilibrium temperature, and this would take centuries to millennials to adapt to. And you plotted the regional surface temperature change normalized by the global mean temperature change over a given period. You would see that different parts of the world are predicted to or projected to warm at different rates at different times in response to the forcing. This is driven by, for example, slow ocean time scales compared to the fast response in the atmosphere of certain clouds or Arctic amplification and so on. And this sort of knowledge is summarized in the IPCC reports, so you can find these online. This is a huge breadth of knowledge summarized very concisely, but because it's so much, it's still very long documents. So these build strongly on the CMAP results, but clearly also on observed data sets. So it tries to synthesize all these different, all the knowledge that we have accumulated in the scientific literature over time. And yeah, here just 3 book covers that come from 3 different working groups working on the latest IPCC AR6 report. So this is the number that we are now in sync with, right? Otherwise, this would be CMAP 5 to AR6. Now it's CMAP 6 to AR6. So these documents can be very long. The physical science basis goes into the science fundamentals, and then there are also working groups, for example, looking into mitigation, so what options are on the table. So if you're interested, I would recommend starting with the summaries for policymakers, because these are quite brief summaries of the highlights. It's a bit dictionary style, but it has become better over the years. It becomes slightly more readable, I suppose. Okay, so I want to give you time back, so I will not talk much more. So next week, the last lecture will be sort of a number of concepts, and I still have to maybe figure out a few of these issues. But one aspect will certainly be weather forecasting using machine learning. So I hope this will be giving you an interesting insight in some current applications. So here just a few summaries. We talked about transformers and the importance of attention mechanisms for learning long-range dependencies effectively. We talked about the TFT architecture that is intrinsically more interpretable, so aims for squaring that with interpretability, stability over long forecast horizons, and so on. And then we talked a little bit about CMIP, what it does, what a massive effort it is, and that you have a vast data archive here for you, for scientists, but also machine learners to explore the predictability of the climate system and, for example, model uncertainty, spread and projections, and so on. Okay, so on this I will end. Are there any questions? No? As always, otherwise post to the discussion board. I still have a few assignments here to collect, but let me stop the recording.